If you were standing on Europa, all you would see is a frozen surface that stretches outward in every direction. The ground beneath you is a solid shell of water, locked in ice, covering the entire surface of this moon of Jupiter. The ice is pale, mostly white with hints of grey, crossed by countless lines that run toward every visible horizon. There is no atmosphere here to speak of, just the thinnest wisp of oxygen molecules drifting above the frozen ground below. The silence is complete, the cold is constant, and the ice has been here for longer than humans have existed on Earth. This is one of the 4 large moons of Jupiter, discovered over 4 centuries ago by Galileo Galilei using his early telescope. Europa is slightly smaller than Earth's moon, measuring about 3,100 kilometers across at its widest point in space. From Earth, it appears as a tiny point of light near the giant planet, visible through even modest backyard telescopes on clear nights. But arriving here, descending toward the surface, reveals a world unlike anything else in our solar system, for many different reasons. The cold strikes first in any consideration of this place, a temperature that defies easy comparison to Earth experiences. At the equator, where conditions are warmest, the surface sits at roughly minus 160 degrees Celsius continuously throughout time. Near the poles, temperatures drop even further, approaching minus 220 degrees in the eternal shadow of certain regions. This cold has persisted for billions of years, and the ice has remained frozen at the surface throughout all that time. You are listening to The Drowsy Astronaut, and tonight we are visiting a frozen world with an extraordinary secret hidden beneath its surface. We will take our time here, exploring slowly and thoroughly, letting each detail arrive at its own pace without any rush at all. If you feel like sharing where you are listening from tonight, the comments are always open for those who wish to connect. For now, though, we simply settle into this distant place and begin to look around at what exists here on Europa. The smoothness of Europa's surface is remarkable when compared to other moons throughout the solar system we have explored. Most moons are heavily cratered, their surfaces pockmarked by billions of years of impacts from asteroids and comets passing through space. Europa has very few large craters, and those that exist are relatively small compared to what we see elsewhere in the cosmos. This smoothness tells scientists something important. The surface is geologically young, constantly renewed by processes operating from below the ice. The relative lack of craters suggests the surface we see today is perhaps only 40 to 90 million years old, at most. In geological terms, this is quite recent, a mere moment compared to the 4.5 billion year age of the solar system. Something is erasing the craters, refreshing the surface, covering over the evidence of ancient impacts, with new material continuously arriving. That something involves the ice shell and what lies beneath it, a subject we will explore as our journey continues forward. The ice shell that covers Europa is not thin by any earthly standard of measurement for ice thickness anywhere. Estimates suggest the frozen layer extends downward for perhaps 15 to 25 kilometers before giving way to something else entirely below. Some models suggest the ice could be even thicker in certain regions, perhaps 30 kilometers or more in places around the moon. This is ice on a scale that dwarfs anything on Earth. a frozen shell covering an entire world completely without interruption. The color of the surface varies across Europa's face in patterns that have fascinated scientists for decades of observation now. Most of the ice appears white or pale gray, the color of clean water ice reflecting sunlight back into space continuously. But scattered across this pale surface are patches and streaks of brownish-red material, concentrated in certain regions around the moon. These discolorations are not random stains, but rather clues about what might be rising from below the ice. The reddish-brown material is believed to contain salts and other compounds that originate from beneath the frozen surface layer. Scientists have detected signatures of magnesium sulfate and other salts in these darkened regions using spectroscopy from spacecraft far above. The coloration may come from these salts being altered by radiation from Jupiter's intense magnetic field, bombarding the surface continuously. Whatever the exact chemistry, the stains mark places where material from below has reached the surface somehow over time. Jupiter hangs in the black sky above Europa, enormous and ever-present, dominating the view from this small moon completely. From the surface, Jupiter appears about 24 times larger than the full moon does from Earth's night sky perspective. The planet's bands and storms are visible to the naked eye from here, a gas giant so close that its influence shapes everything about this moon. That influence is gravitational, pulling on Europa with forces that have profound consequences for the hidden world beneath the ice. The sky above Europa is almost entirely black, even during the daytime hours when the distant sun provides illumination. There is essentially no atmosphere to scatter light and create a blue or hazy sky like we experience on Earth. Stars remain visible even when the sun is above the horizon, pinpricks of light against the blackness surrounding this frozen world. The sun itself appears much smaller than from Earth, about 1/5 the size, providing only about 4% of the light. The weak sunlight that does reach Europa provides little warmth to the frozen surface ice, covering the entire moon. At this distance from the sun, roughly 5 times farther than Earth, solar energy is spread thin across vast space. The ice absorbs some of this energy, but the intense cold of the surrounding environment radiates heat away faster than sunlight provides it. The surface remains frozen, not in spite of sunlight, but because the sun is simply too far away to matter much. Europa orbits Jupiter in about 3.5 Earth days, a relatively quick circuit around the giant planet nearby. This orbit keeps one face of Europa permanently aimed toward Jupiter, just as our moon always shows the same face to Earth. From the Jupiter-facing hemisphere, the giant planet never sets, always hanging in the same position in the black sky above. From the opposite hemisphere, Jupiter is never visible at all, hidden forever below the curved horizon of the moon. The orbital period also means that Europa experiences both day and night, but on a timescale different from Earth's daily cycle. One complete day-night cycle on Europa takes about 3.5 Earth days, matching the orbital period around the planet. During the long day, weak sunlight illuminates the ice for roughly 42 hours before giving way to equally long night ahead. The temperature barely changes between day and night because so little solar energy reaches this distant world in space. The ice beneath would feel solid and hard if you could somehow stand upon it in a protective suit tonight. At these temperatures, water ice behaves more like rock than the slippery substance we know from Earth's winter season. The ice would not crack under footsteps, would not feel slick or smooth, but rather rough and unyielding beneath boots. Walking across Europa's surface would be walking across a landscape as solid as granite, just made of frozen water. The texture of the surface ice varies considerably from place to place across the moon's frozen exterior, visible from orbit. Some regions appear relatively smooth, plains of ice that stretch for kilometers without significant features interrupting the flatness encountered. Other regions are rough and jumbled, chaotic terrain where the ice has been disrupted and refrozen in complex patterns. Still other areas are dominated by ridges and lines, features that cross the surface in patterns we will explore in detail soon. The ice we see at the surface is ancient in one sense, but young in another, paradoxical way for observers to consider. The water molecules themselves have been here for billions of years, part of Europa since the moon formed long ago. But the surface we observe has been reworked, renewed, and reshaped within the last few tens of millions of years, continuously. The ice is recycled, old surface giving way to new material from below, the frozen shell breathing slowly over geological time. This surface that seems so static and frozen is actually part of a dynamic system that operates on timescales beyond daily observation. The ice shell moves and changes, cracking and healing, responding to forces that we will come to understand as our journey continues. For now, we simply rest here on the surface, taking in the cold, the silence, and the strange beauty of this frozen world. The ice stretches to every horizon, and somewhere beneath it lies something remarkable that sets Europa apart from almost every other world. The lines that cross Europa's surface are visible from great distances, dark bands stretching for hundreds of kilometers across the pale ice. These features, called lineae by scientists, form the most distinctive characteristic of this moon's frozen face when viewed from orbit. Some run relatively straight, while others curve gently across the surface, following patterns that reflect underlying forces at work. The lines crisscross each other in complex networks, older features cut by younger ones in a readable record of geological history. The darkness of these lines comes from material that differs from the clean water ice surrounding them on all sides. The brownish-red coloration concentrated in these bands suggests salts and other compounds have been deposited along these features over time. This material appears to have risen from below, carried upward through cracks in the ice as they formed and healed. The lines are not simply cracks, but channels through which the interior of Europa has communicated with the surface. Double ridges are the most common type of linear feature found on Europa's frozen surface across all regions studied. These appear as pairs of parallel raised ridges running side by side, with a shallow valley or trough between them typically. The ridges can rise 100 to 300 meters above the surrounding ice plain, substantial features by any standard of measurement. They extend for hundreds of kilometers across the surface, some of the largest continuous features on this small moon. The formation of double ridges involves processes that scientists have studied and modeled using our understanding of ice physics. When the ice shell cracks due to tidal stresses from Jupiter's gravity pulling on the moon, a fracture opens at the surface. Material from below, perhaps warm ice or even liquid water, rises into the crack and begins to accumulate along its edges. As this material freezes and builds up over time, it creates the raised ridges on either side of the original crack line. The tidal forces responsible for cracking the ice come from Jupiter's enormous gravitational influence on this close orbiting moon. Europa's orbit is not perfectly circular, but slightly elliptical, meaning its distance from Jupiter varies during each 3.5-day circuit. When Europa is closer to Jupiter, the gravitational pull is stronger, and when farther, the pull is weaker throughout the orbit. This variation causes the entire moon to flex, stretching and relaxing by about 30 meters every orbit continuously, forever. This flexing is like squeezing a stress ball repeatedly, and over millions of years, it has cracked the ice in patterns we can now observe. The cracks form where the stress is greatest, creating the linear features that dominate Europa's appearance from any vantage point. The pattern of cracks changes with latitude, reflecting the geometry of how tidal forces affect different regions of the moon. Near the equator, the stresses differ from those near the poles, and the patterns of lineae reflect these differences. The material that fills the cracks and creates the dark bands is believed to originate from the subsurface ocean beneath the ice. When cracks open, this material rises through the ice shell, carrying salts and other compounds from the water below upward. As it reaches the surface and freezes, it deposits these substances along the fracture, creating the visible dark coloration observed. The lines are essentially windows into the chemistry of Europa's hidden ocean, samples brought to the surface naturally over time. Some of the lines on Europa show evidence of lateral movement, similar to the motion that occurs along faults on Earth. Scientists can observe places where features on one side of a line have shifted relative to features on the other side of the same line. This indicates that the ice blocks have moved horizontally, sliding past each other while the crack was open or active below. The ice shell is not static but mobile, blocks shifting position over geological time as forces continue acting upon them. The pattern of intersecting lines allows scientists to determine the relative ages of different features across the surface visually. A line that crosses over another line must have formed later, cutting through the older feature after it already existed. By tracing these relationships across the surface, researchers can reconstruct the sequence of events that shaped Europa's face. The lineae form a geological record, each line a chapter in the ongoing story of this dynamic frozen world. Some of the oldest visible lines have been crossed by dozens of younger features, indicating they formed very early in the observable history. These ancient lines are often faint and degraded, partially obscured by younger features and surface processes occurring since their formation. The youngest lines appear fresh and sharp, their edges well-defined, their coloration still distinct against the surrounding ice surface. The story written in these lines spans tens of millions of years of continuous geological activity on Europa. The lines also vary in their width and character across different regions of Europa's surface geography, observed from orbit. Some are narrow, just a few kilometers across, appearing as thin, dark threads against the pale ice surrounding them. Others are wide bands tens of kilometers across, major features that dominate their local landscape completely for observers. The width may relate to how long the crack remained active, how much material rose through it, or other factors scientists continue to study. The continuous activity that creates and maintains these features indicates that Europa's ice shell is alive in a geological sense. Unlike dead worlds with ancient, unchanging surfaces, Europa is constantly being reshaped by ongoing processes operating even now. The tidal flexing continues with every orbit. New cracks may be forming while old ones heal elsewhere across the surface. This activity suggests that whatever lies beneath the ice remains dynamic, providing the heat and material that drive surface changes. The lines on Europa tell a story of a world connected to its interior in ways that static surfaces cannot reveal. Every dark band represents a moment when the depths communicated with the surface, when material from below reached the frozen shell. The patterns reveal the forces at work, the rhythms of tidal flexing, the ongoing dance between Jupiter and its frozen moon. These lines are not scars but messages, written in ice and salt across the face of this distant world for us to read. Not all of Europa's surface consists of orderly lines and smooth ice plains stretching toward the distant horizons. Some regions have been dramatically disrupted, the ice shattered and jumbled into chaotic terrain unlike anything seen on other worlds. These areas, simply called chaos terrain by scientists, cover perhaps a quarter to nearly half of Europa's visible surface. They represent the most dramatic evidence that something dynamic is happening beneath the frozen shell covering everything. Connemara chaos is perhaps the most famous and well-studied example of these disrupted regions on Europa's surface. This area spans roughly 120 by 170 kilometers, a substantial region of broken and refrozen ice. Within this zone, large blocks of ice have tilted, rotated, and shifted from their original positions into new configurations. The orderly pattern of lineae that crosses surrounding regions is completely disrupted within this chaotic zone. Observed, the appearance of chaos terrain resembles sea ice on Earth that has been broken up and refrozen in new arrangements. Large blocks, some as much as 10 kilometers across, sit at odd angles, their original positions clearly disturbed by some force. Dark material fills the gaps between blocks, a matrix that formed after the disruption event that created this chaos region. The blocks themselves can sometimes be fitted back together, like puzzle pieces, revealing exactly how they moved and rotated. The formation of chaos terrain requires something to disrupt the ice from below, and the most likely candidate is heat. Scientists believe that in some regions, heat from the interior rises more strongly than in surrounding areas, creating the chaos. This heat warms the base of the ice shell, softening it, or perhaps partially melting it into a slush-like consistency, temporarily. The surface ice blocks lose their solid foundation and begin to float, rotate, and shift before everything refreezes again. The process may unfold over thousands of years, a slow-motion catastrophe by human standards, but rapid in geological terms. First, heat from below begins warming the ice, weakening it from the bottom upward toward the surface above. Then the surface layer begins to crack and separate into distinct blocks as the foundation beneath becomes unstable. The blocks float and drift, rotating to new positions before the heat source diminishes, and everything freezes solid once again. The dark matrix material between blocks is particularly interesting for understanding what happened during chaos formation events. This material is younger than the blocks themselves, having formed after the disruption was already underway or complete. It likely represents material from deeper in the ice shell, or perhaps from the ocean itself rising between the separated blocks. The chemistry of this matrix material may provide direct information about what exists beneath Europa's frozen surface layer. The reddish-brown coloration is particularly intense in chaos regions, more so than in the linear features crossing other areas nearby. This suggests that chaos formation brings more subsurface material to the surface than the simple cracking that creates linear features. The chaos regions may represent places where the barrier between the ocean and surface was thinnest or was breached most completely. If any surface material on Europa came directly from the ocean, chaos terrain is the most likely source. Some scientists have proposed that chaos terrain forms when subsurface water pockets melt through the base of the ice shell entirely. These water pockets, sometimes called lenses, might form when heat concentrates in particular regions of the ice for various reasons. As the pocket grows, it rises toward the surface, eventually reaching a point where the overlying ice cannot support its weight above. The ice collapses into the water, floats, rotates, and eventually refreezes as the water is exposed to the cold surface environment. The implications of chaos terrain for Europa's habitability are significant and worth considering carefully here tonight. If these regions represent places where subsurface water reached near the surface, they are places where ocean chemistry is accessible for study. Spacecraft might be able to sample chaos terrain material and learn about the ocean without ever penetrating the ice directly. Future missions might specifically target chaos regions for this reason, seeking accessible samples from the hidden world below. The distribution of chaos terrain across Europa's surface is not uniform, but concentrated in certain regions of the Moon. Some areas have extensive chaos coverage, while others remain dominated by linear patterns with minimal disruption occurring. The reasons for this uneven distribution are not fully understood, but may relate to variations in heat flow from the interior. Regions with more heat beneath them might be more prone to chaos formation than cooler regions elsewhere on Europa. The age of chaos terrain varies, with some regions appearing relatively fresh, while others show signs of subsequent modification. Younger chaos regions have sharp block edges and well-defined matrix boundaries between displaced sections of ice surface. Older regions have been softened by further surface processes, their edges degraded, their matrix materials altered by ongoing exposure. The chaos terrain record stretches back millions of years, with events occurring at different times across the Moon's history. Looking across a chaos region from a vantage point above the surface reveals a landscape of extraordinary visual complexity. Blocks of various sizes and orientations create a jumbled terrain that would be difficult to traverse on foot today. The dark matrix forms valleys and low areas between the tilted blocks, a contrasting color against the pale ice pieces. This is terrain that speaks of violence and disruption, of forces powerful enough to break a frozen world into pieces temporarily. Yet the chaos terrain also speaks of connection, of a surface intimately linked to what lies beneath the frozen shell. Every chaos region represents a moment when the depths came close to the surface, when the hidden ocean nearly revealed itself directly. The blocks and matrix material are samples from below, brought up by processes we are only beginning to understand fully now. These disrupted regions are not just geological curiosities, but potential windows into the habitability of Europa's hidden ocean world. Beneath all of this frozen surface, beneath the chaos terrain and the lineae, beneath the ice shell that has covered this moon for billions of years, lies an ocean. This is not a small sea or a modest lake, but a global ocean that encircles the entire moon beneath its frozen roof. The ocean contains more water than all of Earth's oceans combined, perhaps 2 to 3 times more by volume conservatively estimated. This hidden sea makes Europa one of the most intriguing destinations in the search for life beyond Earth in our solar system. The evidence for this ocean comes from multiple sources, but the most compelling arrived from the Galileo spacecraft in the 1990s. Galileo carried a magnetometer, an instrument designed to measure magnetic fields in the space around Jupiter and its moons. As the spacecraft passed by Europa, it detected a magnetic signature that varied in a way that required a conducting layer below the surface. The most logical explanation for this conducting layer was a salty liquid water ocean beneath the ice. The way this magnetic detection works involves Jupiter's enormous rotating magnetic field sweeping past Europa continuously in space. If Europa had no conducting layer, this sweeping field would simply pass through the moon without creating a measurable response. But Europa does respond, generating an induced magnetic field that changes as Jupiter's field sweeps by during each orbital passage. This response requires electrical currents to flow within Europa, and salty water is an excellent conductor of electricity. Fresh water would not produce this signal because it does not conduct electricity well enough to generate measurable induced fields. The conducting layer must be salty, similar to Earth's oceans, with dissolved minerals and salts that allow current to flow. This immediately tells us something important about Europa's ocean beyond just its existence beneath the ice. The water is not pure, but contains dissolved substances that suggest chemical interaction with rock over time. The size of this ocean is almost beyond comprehension when you try to hold the numbers in your mind tonight. Estimates suggest the ocean may be 60 to 150 kilometers deep beneath an ice shell of perhaps 15 to 25 kilometers. The total volume of water is roughly 3 times all the water in all of Earth's oceans, lakes, rivers, and ice caps combined. More liquid water exists on this tiny moon than on our entire home planet, with all its blue visible from space. The pressure at the bottom of this ocean would be immense, far beyond anything experienced in Earth's deepest trenches anywhere. At 100 kilometers of water depth, the pressure would exceed 1,000 times Earth's atmospheric pressure at sea level today. Even at 60 kilometers, the pressure would dwarf anything found in Earth's Mariana Trench by a factor of 6 or more. Yet this pressure alone would not prevent chemistry or even life from existing in the deep waters below. The darkness of the ocean is total and permanent, a feature that seems hostile to life as we commonly imagine it. No sunlight reaches even the surface of the ice, except in negligible amounts due to Europa's great distance from our star. Beneath the ice shell, the darkness would be absolute, an ocean that has never experienced a single photon of visible light. Yet darkness alone is not a barrier to life, as we have learned from Earth's own deep-sea ecosystems, thriving far below. The temperature of the ocean is a crucial factor in understanding what this hidden sea might be like inside. The water must be liquid, which means it cannot be as cold as the surface ice that covers it from above. Scientists believe the ocean is kept liquid by heat from within the moon, heat that we will explore in detail soon. The temperature is likely close to freezing near the ice boundary, but possibly warmer near the bottom where heat enters. The interface between the ice shell and the liquid ocean below is a boundary of considerable scientific interest for researchers. This is where frozen water gives way to liquid, where the solid shell meets the sea it has covered for billions of years. The transition may not be sharp but gradual, with slushy ice giving way to cold liquid water over some vertical distance. This boundary is also where any exchange between the surface and ocean must occur through the ice. The ocean has likely existed in some form for most of Europa's history since the moon formed billions of years ago. The heat source that keeps it liquid has operated throughout this time, preventing the water from freezing solid entirely. This means the ocean has had billions of years to develop whatever chemistry exists within its dark waters today. If life is possible in such an environment, it has had ample time to arise and evolve without interruption. We cannot see this ocean directly with any instruments we currently possess in space or on Earth today. The ice shell blocks all direct observation, hiding the water beneath from every telescope and every spacecraft camera available. We know it exists through indirect evidence, through magnetic measurements and surface geology that require an ocean to explain. But the ocean itself remains hidden, a sea we know is there, but cannot yet observe directly with our technology. The presence of this vast ocean raises questions that drive scientific exploration and capture human imagination completely. What is the chemistry of this water after billions of years of contact with rock and ice without interruption? Does the ocean circulate, with currents carrying water from place to place beneath the frozen roof above? And the question that motivates so much of our interest: could anything live in those dark waters far from the sun? These questions will guide our exploration as we continue through this journey tonight together on this channel. The ocean is the heart of what makes Europa special among all the worlds in our solar system beyond Earth. Everything about the surface, the chaos terrain, the lineae, the fresh appearance, all of it connects to this hidden sea below. For now, we simply hold the reality of this ocean in our minds. A sea larger than Earth's, hidden beneath ice, waiting in darkness. The ocean beneath Europa's ice remains liquid, despite the moon's great distance from the sun's warming light. At this distance, 5 times farther than Earth, solar heating is far too weak to prevent ice from freezing solid permanently. Something else must provide the heat that keeps this vast ocean from becoming a solid ball of ice throughout. That something is the gravitational influence of Jupiter, the giant planet around which Europa endlessly orbits in space. Jupiter is the largest planet in our solar system, containing more mass than all other planets combined together. Its gravitational influence extends far into space, affecting everything that orbits near it, with immense tidal forces acting constantly. Europa orbits relatively close to Jupiter, completing one circuit every 3.5 Earth days, without stopping ever. This proximity means Jupiter's gravity pulls strongly on Europa throughout its orbit around the massive planet nearby. The key to tidal heating lies in the shape of Europa's orbit, which is not perfectly circular, but slightly elliptical overall. This means Europa's distance from Jupiter varies during each orbit, sometimes closer and sometimes farther from the giant. When closer, Jupiter's gravity pulls more strongly on the Moon, and when farther, the pull is weaker than average. This variation in gravitational pull causes Europa to flex, stretched and compressed as it moves around the planet. The stretching amounts to about 30 meters over each orbit, a small number compared to the Moon's 3,000-kilometer diameter. But this flexing happens continuously, every 3.5 days, and has been happening for billions of years without interruption. The repeated flexing generates friction within Europa's interior, and friction produces heat as a direct physical consequence always. This heat, called tidal heating, is what keeps the ocean liquid despite the distant cold of outer space. The mechanism is similar to what happens when you repeatedly bend a piece of metal wire back and forth quickly. The wire becomes warm where you are bending it, the mechanical stress being converted to thermal energy through friction. Europa is being bent by Jupiter's gravity, and the interior of the Moon heats up from this continuous flexing over time. The heat flows outward from the interior, warming the ocean and keeping it from freezing solid entirely throughout. Europa's slightly elliptical orbit is maintained by gravitational interactions with the other Galilean moons orbiting Jupiter nearby. Io, the innermost large moon, and Ganymede, the outermost, are locked in an orbital resonance with Europa between them. For every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1, in perfect synchronization. This resonance keeps Europa's orbit from becoming circular, which would eliminate the tidal variation and eventually stop the heating. The amount of heat generated by tidal flexing is substantial, comparable to the heat generated by radioactive decay within Earth's interior today. Estimates suggest Europa produces somewhere between 1 trillion and 100 trillion watts of tidal heating power continuously. This is enough energy to maintain a liquid ocean beneath the ice for billions of years, without any help from sunlight. The heat flows upward from the rocky interior, through the ocean, and into the ice shell above, continuously. Io, Europa's inner neighbor, provides a dramatic demonstration of what extreme tidal heating can accomplish over time. Io is the most volcanically active body in the solar system, covered with erupting volcanoes and lava flows constantly appearing. This intense volcanism is driven by tidal heating from Jupiter, far more extreme than what Europa experiences closer in. Io's orbit is even more eccentric, and its proximity to Jupiter even closer, generating far more internal heat than Europa. Europa's tidal heating is gentler than Io's, which is fortunate for the prospects of a stable liquid water ocean below. Too much heat would make the ocean boil or prevent ice from forming at the surface as a protective layer. Too little would allow the ocean to freeze solid, eliminating the liquid water that makes Europa so interesting today. Europa exists in a middle ground, receiving enough heat to maintain liquid water, but not so much as to destabilize the system. The heat flows from below upward, warming the ocean from the bottom rather than from the top, as solar heating would do. This is similar to how Earth's oceans are heated from above by sunlight, but inverted completely in this case. The warmest water in Europa's ocean is likely near the bottom, closest to the rocky interior where heat originates. The coldest water is near the top, against the ice shell that insulates the ocean from the frozen surface above. This inverted temperature gradient may drive circulation patterns within the ocean that mix water from different depths together. Warm water rising from the bottom and cool water sinking from below the ice could create currents beneath the frozen shell. These currents might distribute heat and chemicals throughout the ocean, carrying material from place to place continuously over time. The ocean is likely not static but moving, though the nature of this circulation remains unknown without direct observation. The tidal heating also affects the ice shell itself in ways that contribute to the surface features we observe from orbit. Heat flowing upward from the ocean warms the base of the ice, keeping it relatively soft compared to the cold surface. This warmer, softer ice at depth may flow slowly, convecting over millions of years, like a very slow lava lamp motion. The surface ice cracks under tidal stress, while the deeper ice flows, creating the complex geology we see from spacecraft above. The continuous nature of this heating is what makes Europa special compared to worlds that might have had oceans in the ancient past. Mars may have had liquid water billions of years ago, but that water froze or escaped long ago without ongoing heat. Europa's ocean has been liquid continuously since the Moon formed, heated by the same tidal forces throughout all that time. This stability matters enormously for the potential development of life over billions of years of chemical evolution. The engine of heat that powers Europa's ocean will continue operating as long as the orbital resonance with Io and Ganymede persists. This resonance is stable over very long timescales, meaning the heat source will not disappear in any foreseeable future ahead. Europa's ocean will remain liquid for billions of years to come, continuing the conditions that make this moon so fascinating to scientists today. The hidden sea will persist, warmed from below by the patient gravitational massage of the giant planet it orbits. The ocean that fills Europa's interior does not simply end in open water at its lower boundary beneath everything else. Somewhere below the liquid water lies a floor, a rocky bottom where the sea meets the solid interior of the moon. This ocean floor sits perhaps 60 to 150 kilometers below the ice surface, far above it in the darkness. What happens at this boundary between water and rock may be the most important factor in determining whether Europa could harbor life. The rocky interior of Europa is believed to be similar in composition to Earth's oceanic crust in many of its basic properties. Silicate rocks, rich in minerals like olivine and pyroxene, likely make up the bulk of this rocky layer surrounding the core. These rocks have been in contact with the ocean water for billions of years, allowing chemical reactions to occur continuously over time. The interaction between rock and water can release energy and nutrients that might support chemical or biological processes below. The tidal heating that warms the ocean originates primarily in this rocky interior where flexing generates friction and heat. This means the ocean floor is likely the warmest part of Europa's ocean, heated from below by the rocky mantle underneath. Hot water and rock interacting at this boundary could create conditions similar to those found at hydrothermal vents on Earth's seafloor. These vents are places where hot water rises through cracks in the rock, carrying dissolved minerals into the cold ocean. On Earth, hydrothermal vents support thriving ecosystems entirely independent of sunlight, reaching them from the surface, far above. Bacteria and archaea at these vents use chemical energy from reactions between hot water and rock to power their metabolism. These microbes form the base of a food chain that includes tube worms, clams, crabs, and fish, living in complete darkness. The energy comes not from the sun, but from the heat of Earth's interior and the chemistry it drives. The possibility of similar vents on Europa's ocean floor is one of the most exciting aspects of this hidden world for scientists. If hot water is rising through cracks in the rock, it would carry hydrogen and other reduced chemicals into the ocean water. These chemicals could react with oxidants in the water to release energy that organisms might capture and use for life. The same energy that keeps the ocean liquid could potentially power a biosphere on the ocean floor below the ice. The chemistry of these hypothetical vents would depend on the composition of Europa's rocky interior and the water itself together. If the rock contains iron and other reactive metals, reactions with water could produce hydrogen gas continuously at the vent. Hydrogen is an excellent fuel for chemosynthetic organisms, providing energy when combined with carbon dioxide or other oxidants available. The ingredients for this chemistry seem plausible based on what we know about Europa's structure today from various studies. The pressure at Europa's ocean floor would be extreme by any standard we experience on Earth's seafloor, anywhere. At 100 kilometers of water depth, the pressure would exceed 100 megapascals, roughly 1,000 times Earth's surface atmospheric pressure. Even at 60 kilometers, the pressure would be extraordinarily high compared to any environment on our home planet today. Yet pressure alone does not prevent life, as we know from organisms living in Earth's deep ocean trenches, successfully. The darkness at the ocean floor would be absolute, no different from the darkness throughout the rest of the ocean above. No sunlight could ever penetrate the ice shell, let alone reach the bottom of a 100-kilometer deep ocean below. Yet darkness is not a barrier to the chemosynthetic life found at Earth's vents, which have never relied on sunlight for energy. The energy comes from chemistry, which can proceed in any level of illumination without requiring photons at all. The temperature at the ocean floor might be surprisingly warm compared to the near-freezing water above it in the ocean. If hydrothermal activity is occurring, the water near vents could be quite hot, perhaps tens or hundreds of degrees Celsius. The surrounding ocean would be colder, creating a temperature gradient that could drive circulation and mixing continuously. Life on Earth exploits these temperature gradients, with different organisms adapted to different temperature zones near vents. We cannot observe the ocean floor directly with any technology currently available to astronomers and planetary scientists. The ice shell blocks all forms of electromagnetic radiation, including radar that might otherwise penetrate some distance into the ice. Seismometers on the surface might detect signals from the ocean floor, but we have not yet landed any instruments on Europa. Everything we know about the ocean floor is inferred from models and comparisons to similar environments on Earth. The possibility of hydrothermal activity on Europa's ocean floor makes this boundary scientifically compelling for multiple reasons. This is where chemical energy could be released, where nutrients could enter the water, where conditions might favor life's origin. If life exists on Europa, the ocean floor is perhaps the most likely place to find it, thriving in the deep. The floor is where the action happens, where heat meets water, where chemistry has the greatest opportunity to become biology. Future exploration might eventually focus on reaching this deep boundary to search for signs of activity or even life. Such a mission would be extraordinarily challenging, requiring melting through kilometers of ice and descending through the ocean below. The technology for such exploration does not yet exist, but is being developed for potential future missions ahead. The ocean floor of Europa represents perhaps the ultimate target for astrobiology, a place where answers might finally await discovery. The question of life on Europa hangs over every aspect of our exploration of this frozen moon tonight and always. Could something live in that dark ocean powered by heat from below, isolated beneath kilometers of ice from everything else? This question drives scientific interest in Europa and motivates the missions we send to study it closely over time. Yet the question itself requires careful consideration of what we mean by life and what Europa actually provides for it. Life, as we understand it, requires certain fundamental ingredients to exist and persist anywhere in the universe around us. Liquid water is considered essential, serving as the medium in which biochemical reactions occur in every living thing on Earth. Energy is required to power metabolism, whether from sunlight, chemical reactions, or other sources available to organisms locally. And the right chemistry must be present, the elements and compounds from which life can build its complex molecular structures. Europa appears to provide at least two of these three requirements with some confidence based on available evidence today. The liquid water ocean is almost certainly present, revealed by magnetic measurements and implied by surface geology observations. Energy is available from tidal heating, and chemical energy might be released at a water-rock interface on the ocean floor. The chemistry is less certain but plausible, with salts confirmed and other compounds likely present in the water. The comparison to Earth's deep-sea hydrothermal vents provides a template for thinking about life on Europa's ocean floor realistically. On Earth, these vents host ecosystems that are entirely independent of sunlight, powered by chemical energy from the planet's interior instead. Bacteria and archaea at vent sites use chemosynthesis, harnessing energy from reactions between hot water and rock materials present. If similar vents exist on Europa, similar metabolic processes might be possible for any organisms present there. Life at Earth's vents has been flourishing for as long as the vents have existed. Billions of years, according to geological evidence. These organisms have evolved to thrive in conditions once thought impossible for life. Extreme heat, extreme pressure, and complete darkness. The discovery of this deep-sea life has expanded our understanding of where life can exist and how it can function. It provides hope that Europa's dark ocean might not be as hostile to life as it might first appear. However, the existence of suitable conditions does not guarantee that life has actually arisen on Europa at all. On Earth, life originated only once that we can determine, and all living things descend from that single origin event. We do not know how difficult this origin was, whether it was a nearly inevitable chemical process or an extremely rare accident. If origin events are rare, Europa might have the right conditions, but still be completely sterile without life. The time available for life to arise on Europa has been substantial, spanning most of the moon's 4.5 billion year history. The ocean has likely been liquid for most of this time, providing continuous conditions for chemical evolution to proceed naturally. On Earth, life appeared relatively quickly after conditions became suitable, within the first billion years of our planet's history recorded. If the same is possible on Europa, life could have originated long ago and might still persist today. Below, the isolation of Europa's ocean from the surface and from space is both a challenge and a protection for any life within. Nothing has ever contaminated the ocean from outside. No impacts or radiation or other disturbances from the harsh surface environment. But this isolation also means that any life would have evolved entirely independently, with no connection to Earth's biology at all. Such life would be truly alien, a second origin that would tell us that life arises whenever conditions permit. The detection of life on Europa, if it exists, would require sophisticated instruments that we have not yet sent to this distant moon. Current missions can only study the surface and infer what lies beneath from indirect measurements and observations above. Detecting life would require either sampling material from the ocean or finding unmistakable biosignatures in surface material from the ice. Neither of these achievements is possible with the missions we have flown or are currently flying to Europa. The question of life remains open, neither answered yes nor no by any evidence currently available to scientists today. Europa might be teeming with microbial life in its dark ocean, or it might be completely sterile despite suitable conditions. Existing, we simply do not know, and this uncertainty is what drives our desire to explore further and learn more. The question is profound. Are we alone, or does life arise wherever conditions permit throughout the cosmos? The search for life on Europa is not about finding intelligent beings or complex organisms like those on Earth's surface. Any life in Europa's ocean would almost certainly be microbial, single-celled organisms similar to bacteria or archaea on Earth today. These would be simple life forms, adapted to the extreme conditions of the deep ocean environment over billions of years. Yet even simple life would be a discovery of immense significance, proving that life is not unique to our home world. The implications of finding life on Europa would extend far beyond this one small moon orbiting Jupiter in the outer system. It would suggest that life is common in the universe, arising wherever water, energy, and chemistry come together appropriately. The universe contains billions of potentially habitable worlds, and if life arose independently on Europa, it probably arose elsewhere too. We would no longer be asking whether we are alone, but rather how much company we have throughout the cosmos around us. The spacecraft that revealed Europa's secrets to us arrived at Jupiter in 1995, after a journey of 6 years from Earth. The Galileo mission was designed to study Jupiter and its moons, spending 8 years in orbit around the giant planet continuously. During that time, it made 12 close flybys of Europa, each pass revealing new details about this intriguing frozen world nearby. What Galileo discovered transformed our understanding of Europa from a curiosity to a prime target for astrobiology research. The journey to Jupiter had been long and complicated, involving gravity assists from Venus and Earth to gain enough speed. Galileo was launched from the Space Shuttle Atlantis in October 1989, beginning its extended cruise through the inner solar system. By December 1995, it had arrived at Jupiter, entering orbit around the giant planet to begin its primary mission observations. The spacecraft would remain active until 2003, far exceeding its original planned mission duration. significantly. The instruments aboard Galileo were designed to study all aspects of the Jovian system from multiple vantage points during the mission. Cameras captured images of Jupiter's atmosphere and the surfaces of its many moons in visible and infrared light wavelengths. Spectrometers analyzed the composition of surfaces and atmospheres by measuring how they absorbed and reflected light from the sun. And the magnetometer measured magnetic fields, detecting the subtle variations that would reveal Europa's hidden ocean beneath the ice. The magnetometer discovery was perhaps the single most important finding of the entire Galileo mission for future exploration purposes. As the spacecraft passed by Europa, it detected a magnetic field that varied in a way that required explanation beyond simple coincidence. The variation matched what would be expected if a conducting layer existed beneath the surface, responding to Jupiter's rotating magnetic field. The most logical explanation was a salty liquid water ocean, conducting electricity as Jupiter's field swept past continuously. This finding changed everything about how scientists thought about Europa and its potential for habitability immediately. Before Galileo, Europa was suspected to have interesting geology, but a global ocean was not confirmed by observations. After Galileo, the ocean became virtually certain, and Europa became one of the most important targets for astrobiology research anywhere. The search for life beyond Earth had a new prime destination, a world with abundant liquid water hidden beneath the ice. The images returned by Galileo revealed the surface features we have discussed: the lineae, the chaos terrain, the smooth young ice. Each image showed new details about this complex surface, a world constantly being reshaped by forces from below the frozen shell. Scientists could trace the patterns of cracking and healing, reading the history of tidal stress written across Europa's frozen face. The geology confirmed what the magnetometer had detected. This was a dynamic world with an active interior driving surface changes. The closest approach Galileo made to Europa brought it within 201 kilometers of the surface, remarkably close considering the spacecraft. At this distance, the cameras could resolve features just a few meters across, revealing details impossible to see from Earth. The images showed the texture of the ice, the structure of ridges, the complexity of chaos terrain at close range. Each flyby added to the growing dataset, building our understanding piece by piece over years of observation. Galileo also detected substances on Europa's surface that originated from below the ice through spectroscopic analysis. The salts visible in lineae and chaos regions were identified through their spectral signatures in reflected sunlight observations. The presence of these salts confirmed that material from the subsurface ocean was reaching the surface somehow continuously. The surface was not just frozen water, but a record of ocean chemistry, accessible for study without penetrating the ice. The mission also detected hints that Europa might occasionally release material into space through plumes or vents erupting. These hints were not conclusive from Galileo's data, but later observations would strengthen the evidence for occasional water vapor ejections. If such plumes exist, they would offer a way to sample ocean material without landing on the surface. Or drilling. A spacecraft could simply fly through the plume and analyze the ejected water and its contents directly above. The end of the Galileo mission came in September 2003, when the spacecraft was deliberately crashed into Jupiter's atmosphere, intentionally. This decision was made to prevent any possibility of the spacecraft eventually crashing into Europa and contaminating the Moon unintentionally. If life exists on Europa, introducing Earth microbes could confuse future searchers or even harm an alien ecosystem below the surface. The deliberate deorbit protected Europa's pristine ocean from potential contamination by our spacecraft and its earthly cargo. The legacy of Galileo continues to shape our exploration of Europa decades after the mission ended its final operations. Every current and planned mission builds on what Galileo discovered about this ocean world orbiting the giant planet nearby. The questions Galileo raised about habitability, ocean chemistry, and potential life drive the scientific goals of new spacecraft being designed. Galileo showed us a world worth exploring, and we have been planning the next steps ever since its observations concluded. The data from Galileo is still being analyzed today, revealing new details as scientists develop better techniques for interpretation. Old images are being reprocessed with modern software, extracting information that was not accessible when the data first arrived on Earth. The mission that ended 2 decades ago continues to teach us about Europa through its archived observations, stored carefully. Galileo's gift to science keeps giving, even as new missions prepare to build on its foundation of discovery. A new spacecraft is now on its way to Europa, designed specifically to answer the questions that Galileo raised about this ocean world. Europa Clipper launched in October of 2024, beginning a journey that will take it to Jupiter by April of 2030. This mission is the most ambitious exploration of Europa ever attempted, carrying sophisticated instruments designed to probe the Moon's secrets thoroughly. When it arrives, Clipper will conduct dozens of close flybys, building the most detailed portrait of Europa ever created. The name Clipper refers to the mission's approach of making multiple fast passes rather than orbiting Europa directly, continuously. Jupiter's radiation environment is extremely harsh, and spending too much time near the planet would damage the spacecraft's electronics progressively. By flying in and out quickly, Clipper minimizes its exposure to radiation while still gathering data during each close approach. This strategy will allow the mission to operate for years, making approximately 50 close flybys of Europa over its duration. The spacecraft itself is the largest NASA has ever built for a planetary science mission launched to another world. With its solar panels fully deployed, Clipper spans about 30 meters, an enormous structure designed to capture weak sunlight at Jupiter's distance. The size reflects the power requirements of the sophisticated instrument suite and the communication systems needed to send data back. This is a spacecraft built for a thorough, detailed investigation of a world that demands careful study over extended time. The instrument suite aboard Europa Clipper is designed to study every aspect of the Moon that can be observed from orbit above. Cameras will image the surface at resolutions higher than Galileo achieved, revealing features as small as half a meter across. Spectrometers will analyze the composition of surface materials, identifying minerals, ices, and organic compounds if present on the surface. These optical instruments will map Europa's surface in unprecedented detail over the course of the mission's many flybys. Perhaps the most anticipated instrument is the ice-penetrating radar, designed to peer beneath the surface for the first time ever. This radar will send pulses of radio waves down into the ice shell, detecting reflections from boundaries within and below the frozen layer. It should be able to measure the thickness of the ice shell and potentially detect subsurface water pockets if they exist. The radar will reveal the three-dimensional structure of Europa in ways no previous instrument could accomplish. A thermal emission imaging system will map temperatures across Europa's surface, searching for warm spots that might indicate recent activity. If warm ice or water is close to the surface anywhere, it should appear warmer than surrounding areas in thermal images. These warm spots would be prime targets for future exploration, places where the ocean might be most accessible from above. The thermal mapper will help prioritize locations for any future landing or drilling missions being planned. The magnetometer aboard Clipper is more sensitive than Galileo's, designed to characterize the ocean's properties in greater detail now. By measuring how the magnetic field responds to Jupiter's influence, scientists can determine the ocean's depth, salinity, and conductivity more precisely. These measurements will tell us much about the ocean's chemistry and structure, without ever sampling the water directly below. The ocean that Galileo discovered will finally have its properties measured accurately for the first time by the new spacecraft. Europa Clipper will also search for plumes, water vapor jets that may occasionally erupt from the surface into space. If such plumes exist, they would offer a remarkable opportunity to sample ocean material without landing on the surface directly. The spacecraft could fly through a plume and analyze the ejected water and any particles it contains on board. This would be the most direct access to ocean material we could hope for, without actually drilling through the ice. The mission's science goals focus on understanding Europa's habitability, rather than directly detecting life if present below. Clipper is designed to determine whether Europa has the conditions necessary for life to exist in its hidden ocean. It will measure ice thickness, ocean depth, surface chemistry, and energy availability to assess habitability comprehensively and thoroughly. The question of whether life actually exists would be left for future missions, perhaps a lander or even a submarine. The journey to Jupiter takes about 5.5 years, with Clipper using gravity assists from Mars and Earth along the way. The spacecraft will enter orbit around Jupiter in April of 2030, beginning its science mission shortly after arrival there. The primary mission is planned to last 4 years, with possible extensions if the spacecraft remains healthy after initial objectives. By the time Clipper finishes, we will know more about Europa than about any other moon besides our own. The data from Europa Clipper will shape the next generation of missions to this ocean world and inform our understanding completely. If the ice is thin enough, in some locations, a lander might be able to access ocean material relatively easily for sampling. If plumes are confirmed and characterized, a dedicated mission could fly through them repeatedly to analyze their composition thoroughly. Clipper will provide the reconnaissance needed to plan humanity's next steps in exploring this remarkable frozen world far away. The wait for Clipper's arrival at Jupiter will last several more years, a long time by human standards, but brief by cosmic measures. While we wait, scientists continue analyzing Galileo's data and developing new theories about Europa's structure and potential habitability. The anticipation builds as launch recedes into the past and arrival approaches in the future. steadily ahead. Europa has waited billions of years in silence. It will continue waiting until Clipper arrives to begin revealing its secrets. The ice shell that covers Europa is not simply a frozen barrier between us and the ocean, but a dynamic layer in its own right. This ice has thickness, structure, and motion that affect everything about Europa's surface, and our ability to explore what lies beneath. Understanding the ice shell is essential for any future attempt to access the ocean directly through drilling or melting. The shell is the gatekeeper, and we must understand it before we can hope to pass through to the water below. The thickness of the ice shell remains uncertain, despite decades of study and speculation by planetary scientists worldwide. Estimates range from as thin as a few kilometers to as thick as 30 kilometers or more, depending on models used. Some regions may be thicker than others, with variations related to heat flow and tidal stresses across the Moon. Europa Clipper's ice-penetrating radar will finally provide direct measurements of ice thickness across the surface map. The structure of the ice is likely layered with different properties at different depths throughout the frozen shell above. Near the surface, the ice is cold and brittle, behaving almost like rock under the extreme cold conditions encountered. Deeper down, where temperatures are warmer due to heat from the ocean below, the ice becomes softer and more ductile. This warm ice may flow slowly over time, convecting like a very slow lava lamp circulation pattern. The concept of ice shell convection has important implications for the exchange of material between surface and ocean over time. If warm ice rises and cold ice sinks within the shell, material could be transported from near the ocean to near the surface. This might explain how ocean chemistry reaches the surface to create the brownish stains we observe from orbit above. The ice shell would not be a static barrier, but a slow conduit connecting the two realms together. Some models suggest that liquid water pockets may exist within the ice shell itself, separate from the main ocean below. These pockets, sometimes called water lenses, could form when heat concentrates in particular regions and melts surrounding ice locally. The chaos terrain we discussed earlier might form when such pockets rise toward the surface and partially break through the ice. These lenses would be smaller than the main ocean, but potentially more accessible from the surface above them. The surface of the ice shell is continuously bombarded by radiation from Jupiter's intense magnetic field and trapped particles. This radiation breaks apart water molecules and other compounds, creating new chemical species on the surface, constantly over time. Some of these radiation-produced chemicals might be oxidants that could react with reduced compounds from the ocean to release energy. The surface chemistry, driven by radiation, might be important for any potential biology in the ocean far below. The bottom of the ice shell, where it meets the ocean, is a critical boundary for understanding heat and material exchange. This interface is where freezing and melting occur, where the shell grows thicker or thinner depending on local conditions below. Heat from the ocean melts ice from the bottom, while cold from above causes new ice to form at the interface. The balance between these processes determines the overall ice thickness over geological time. The motion of the ice shell as a unit, sliding over the ocean beneath it, has been detected through careful analysis of surface features. The shell appears to rotate slightly faster than the rocky interior, suggesting it is decoupled from the interior by liquid water This differential rotation takes thousands of years to complete, one full lap, but is detectable through the orientation of surface features. The ice shell floats on the ocean like a vast lid, able to move independently of what lies beneath it. The age of the surface ice, estimated at roughly 40 to 90 million years, tells us about the rate of resurfacing processes operating. This relatively young surface means that the ice is being renewed, with old surface disappearing and new surface appearing continuously over time. The processes driving this renewal involve both tectonic activity, creating lineae, and chaos, terrain disrupting larger areas occasionally. The ice shell is alive in a geological sense, constantly changing even if we cannot observe the changes in real time. Any future mission to penetrate the ice shell would need to account for all these factors affecting the frozen layer structure. The thickness would determine how far a drill or melt probe would need to travel to reach liquid water below. The structure would affect how the probe moves through warm versus cold ice layers, with different properties. The potential water pockets might offer intermediate targets, accessible before reaching the main ocean itself far beneath. The technology to penetrate Europa's ice shell does not yet exist, but is being developed in laboratories on Earth today. Concepts include nuclear-powered melt probes that would slowly sink through the ice, melting their way downward over time. Other concepts involve mechanical drills designed to cut through ice under extremely cold and high-pressure conditions encountered. These technologies are being tested in Earth's ice sheets, preparing for eventual deployment at a world far from home someday. The ice shell of Europa is both a barrier and a preserver, hiding the ocean from view, but also protecting it from space. Nothing from outside has ever reached the ocean, keeping it pristine and uncontaminated throughout all of its history. This pristine state is valuable for science, but also imposes responsibilities on any future exploration we might conduct there. Whatever we send must not contaminate the ocean, preserving it for future study and potentially protecting any life present below. Europa is not alone in harboring a hidden ocean beneath an icy shell in the outer solar system beyond Mars. Several other moons of Jupiter and Saturn, and possibly bodies even farther out, may contain similar subsurface seas waiting. The discovery of so many potential ocean worlds has expanded our understanding of where liquid water can exist in space. Europa is part of a family, a collection of ocean worlds that may be common throughout the universe. Ganymede and Callisto, Jupiter's two largest moons, are also believed to have liquid water oceans beneath their icy surfaces today. These oceans are likely deeper beneath thicker ice shells than Europa's ocean lies, making them potentially harder to access directly. Ganymede's ocean may be sandwiched between layers of ice, with high-pressure ice beneath the water itself at great depth. Callisto's ocean may be buried under 100 kilometers or more of ice and rock combined together. These other Jovian moons receive less attention than Europa, primarily because their oceans are likely less accessible and less hospitable overall. The thicker ice shells reduce the chance of material exchange between ocean and surface. For study purposes, the lack of clear rock-water interfaces may limit the chemical energy available for potential life to utilize below. Europa's thinner shell and direct contact between ocean and rock make it the most promising of Jupiter's moons. Saturn's moon Enceladus has confirmed what scientists suspected about ocean worlds through dramatic direct evidence erupting today. Geysers at Enceladus's south pole spray water ice and vapor into space, material that has been sampled by passing spacecraft. The Cassini mission flew through these plumes and detected water, organic molecules, and salts characteristic of ocean water directly. Enceladus provides proof that ocean material can reach the surface and even escape into space regularly. The plumes of Enceladus have been analyzed in detail, revealing a complex chemistry that suggests a habitable ocean environment exists beneath the frozen surface of this small moon orbiting Saturn, far from the Sun. Hydrogen gas detected in the Enceladus plumes suggests hydrothermal activity on the ocean floor, similar to processes on Earth's seafloors today. This hydrogen could provide chemical energy for microorganisms, if any exist, in that distant water beneath the ice. The presence of silica particles indicates hot water interacting with rock at temperatures above 90 degrees Celsius, down below. Enceladus offers perhaps the most accessible ocean material in the solar system, already spraying samples into space for collection. The moon itself is remarkably small, only about 500 kilometers in diameter, roughly the width of Arizona in size. Despite this small size, tidal heating from Saturn keeps the interior warm enough to maintain liquid water continuously over time. The South Polar region shows the famous tiger stripe fractures, where the plumes emerge through cracks in the ice shell. These warm fractures glow in infrared images, revealing heat escaping from the interior into the cold of space above. Enceladus demonstrates that ocean worlds can be surprisingly small and still maintain liquid water through tidal heating processes ongoing. Size alone does not determine whether a moon can harbor an ocean beneath its frozen exterior surface. Today, the relationship with the parent planet, the orbital mechanics, and the internal composition all play important roles in determining outcomes. Enceladus expands our understanding of where oceans might exist throughout the cosmos, beyond our solar system as well. Titan, Saturn's largest moon, represents a different kind of ocean world, with both familiar and alien characteristics combined. Its surface hosts lakes and seas of liquid methane and ethane, rather than water under its thick, orange atmosphere. These hydrocarbon seas cover parts of the polar regions, mapped by radar through the opaque atmosphere by Cassini spacecraft observations. But beneath Titan's crust may lie yet another water ocean, hidden even deeper than Europa's ocean sits. The surface methane lakes of Titan are the only stable bodies of liquid on any surface in the solar system besides Earth's oceans. These lakes experience weather patterns, including methane rain that falls from the hydrocarbon clouds overhead in the atmosphere. The largest sea, Kraken Mare, is larger than Earth's Caspian Sea and may be hundreds of meters deep in places. Titan offers a strange mirror of Earth, with a liquid cycle based on hydrocarbons rather than water operating continuously. The possible water ocean beneath Titan's surface would be sandwiched between ice layers, heated by the moon's interior warmth. This ocean would be extremely deep beneath the surface, perhaps 50 to 100 kilometers below the visible terrain above. Access to this water would be far more difficult than reaching Europa's ocean, if such access were ever attempted. Titan's complexity makes it fascinating, but also challenging for focused exploration of its potential habitability assessment. Beyond the Saturn system, other moons and even dwarf planets may harbor their own hidden oceans awaiting discovery. Triton, Neptune's large moon, shows signs of geological activity that could indicate internal heat and possibly liquid water below. Pluto itself may have a subsurface ocean that has persisted for billions of years, despite the extreme cold at that distance. The outer solar system appears to be unexpectedly rich in potential liquid water environments beneath icy surfaces. The discovery of so many ocean worlds has fundamentally changed how scientists think about habitability throughout the cosmos today. The traditional habitable zone concept focused on the right distance from a star for liquid water on a planet's surface. Ocean moons, like Europa, show that liquid water can exist far beyond this zone, maintained by tidal heating rather than starlight. The universe may contain far more habitable environments than we once imagined possible before these discoveries. This expansion of potential habitats means that life, if it exists elsewhere, might be more common than surface-focused searches would suggest. Every star with giant planets could have moons with subsurface oceans warmed by tidal forces rather than stellar radiation. These oceans would be invisible to our telescopes, hidden beneath ice, detectable only by close spacecraft examination of targets. The galaxy may be filled with dark oceans we cannot see from our current vantage point on Earth. Europa stands out among these ocean worlds for several reasons that make it particularly compelling for exploration purposes. Its ocean appears to be in direct contact with a rocky seafloor, enabling the water-rock chemistry that might support life forms. The ice shell is relatively thin compared to other ocean moons, making the ocean potentially more accessible for future missions. The surface features suggest active exchange between ocean and surface, possibly bringing ocean material up for study. The radiation environment at Europa is harsh due to Jupiter's powerful magnetic field trapping charged particles nearby continuously. This radiation would quickly damage any spacecraft on the surface and poses challenges for long-duration exploration attempts there. However, the radiation also creates interesting chemistry, breaking apart surface molecules and creating oxidants that might eventually reach the ocean. This oxidant delivery could provide additional chemical energy for any potential biosphere existing below the ice today. Comparing Europa to Enceladus reveals different strengths for each target in the search for life beyond Earth's boundaries. Enceladus offers free samples spraying into space, eliminating the need to drill through ice to reach ocean material directly. Europa offers a larger ocean, more thermal energy, and rock-water contact that may enhance habitability for potential organisms. Both moons deserve continued exploration, and both may eventually reveal whether life exists beyond our home planet. The family of ocean worlds in our solar system suggests that such bodies may be common around other stars as well. Exomoons orbiting giant planets in other stellar systems could easily replicate the conditions we see at Europa and Enceladus today. These moons would be nearly impossible to detect with current technology, invisible to our planet-hunting methods that focus on starlight. Future generations may develop techniques to find these hidden oceans around distant stars throughout our galaxy. For now, Europa remains the primary focus of astrobiology efforts in the outer solar system exploration programs underway. The Europa Clipper mission will provide unprecedented data about this moon's ocean and ice shell characteristics in detail. Future missions may attempt to land on the surface, analyze ice samples, or eventually penetrate the shell to reach water. Each step brings us closer to answering the profound question of whether life exists in that dark, distant ocean. The ocean worlds of our solar system form a quiet family, each member hidden beneath ice, each warmed by internal processes. They orbit their giant planets in silence, their oceans isolated from sunlight, their depths unknown to any observer currently. Whether inhabited or lifeless, these seas represent vast reservoirs of liquid water, far from the traditional habitable zones around stars. Europa is one member of this family, perhaps the most promising, but not the only ocean waiting to be explored. The ocean beneath Europa's ice continues its ancient rhythms regardless of any spacecraft observations or scientific interest from Earth. The water moves in currents we cannot see, driven by forces we can only model with our limited understanding. Heat rises from the rocky seafloor, the ice shell flexes with each orbit, and the endless darkness persists without change. This ocean has existed for billions of years, and will continue for billions more, indifferent to our curiosity about it. The processes occurring in Europa's ocean right now are the same processes that have operated since the moon formed long ago. Tidal heating continues to warm the interior, maintaining the liquid state against the cold of surrounding space continuously. Rock and water interact at the seafloor, exchanging chemicals in reactions that may or may not support living things today. The ice shell creaks and cracks as Europa orbits Jupiter, recording stresses in the patterns visible from above. No human has ever seen Europa's ocean, and no probe has ever touched its water or measured its chemistry directly. Everything we know comes from distant observations, from spacecraft flybys, from measurements of magnetic fields and surface features alone. The ocean remains a theoretical certainty, supported by strong evidence, but still unseen, still untouched, still mysterious below. Our understanding is built on inference, on models, on the careful interpretation of indirect data gathered from far away. This distance between our knowledge and the reality of Europa's ocean is both frustrating and appropriate for our stage of exploration. We are early in the process of understanding this world, still mapping its surface, still characterizing its ice shell structure. The detailed investigation of the ocean itself lies in the future, requiring technologies and missions not yet fully developed today. Patience is inherent to the exploration of worlds so far from home across the solar system. The darkness of Europa's ocean is absolute, a blackness that has never been broken by any light source whatsoever. No sunlight penetrates the ice shell, and no bioluminescence has been confirmed in waters where no observers have ever traveled. The pressure increases with depth, the temperature varies according to proximity to heat sources, and the chemistry proceeds in total darkness. If life exists there, it has evolved in conditions utterly unlike the sun-drenched surface of Earth we know. The silence of that ocean is also complete, or nearly so, with only the sounds that water and ice might make together. The creaking of the ice shell might transmit vibrations into the water below during flexing and cracking events occurring. Hydrothermal vents, if they exist, might produce sounds as hot water meets cold ocean in turbulent mixing zones. But no waves break on shores, no wind stirs the surface, No creatures call to each other in any way we could recognize. The isolation of Europa's ocean from the rest of the universe is nearly total compared to environments we understand. The ice shell separates the water from the vacuum of space, and the radiation bathing the surface continuously above. The distance from Earth makes communication slow and difficult, with signals taking over half an hour to travel each direction. This ocean exists in a kind of cosmic solitude, unreachable for now, knowable only through patient, remote investigation methods. The scientific questions about Europa could occupy researchers for centuries, even if no life is ever discovered there eventually. The ocean's chemistry, circulation patterns, thermal structure, and interaction with the ice shell all merit detailed study over time. The history of the ice shell, the evolution of the surface features, the long-term changes in tidal heating rates deserve investigation. Europa offers a natural laboratory for understanding processes that may be common throughout the universe's many ocean worlds. If life does exist in Europa's ocean, discovering it would be among the most profound moments in human history for understanding. Confirming that life arose independently on another world would suggest that life is common throughout the cosmos, wherever conditions permit. Even simple microbial life would demonstrate that Earth is not unique, that the universe is more alive than our single example indicates. The implications for philosophy, religion, and our sense of place in the cosmos would be immeasurable. If life does not exist there, despite apparently habitable conditions, that finding would also carry significant meaning for our understanding. It might suggest that life's origin is more difficult or improbable than the conditions alone would suggest to observers. Perhaps specific circumstances or events are required beyond the mere presence of water, energy, and chemistry for life's emergence. Understanding why life did not arise, if that proves to be the case, would teach us about our own origins. The uncertainty is part of what makes Europa so compelling to scientists and the public alike who follow these matters. We genuinely do not know whether that ocean is inhabited or sterile after billions of years of existence in darkness. This open question drives the exploration program, motivates the mission designs, and captures the imagination of millions worldwide. The answer awaits future discovery by spacecraft and instruments not yet launched toward this distant moon today. The timeline for answering these questions stretches across decades of careful, methodical exploration by human civilization space programs. Europa Clipper will provide crucial data in the early 2030s after its arrival at Jupiter and commencement of observations. Future lander missions might follow in the 2040s if resources and priorities permit such ambitious undertakings to proceed. Penetrating the ice shell to reach the ocean directly might not occur until the second half of this century at earliest. This long timeline requires a kind of patience that does not come naturally to beings with limited lifespans hoping for answers. The scientists who designed Europa Clipper may not live to see the final answer to the life question resolved. The children born today might be elderly before a probe touches the ocean water itself. Directly for sampling, exploration of the outer solar system operates on timescales that span generations rather than individual careers or lifetimes. Yet the work continues, passed from one generation of scientists and engineers to the next, with care and dedication. The knowledge gained by Galileo informed the design of Europa Clipper's mission architecture, and instrument selections carefully. The data from Clipper will inform whatever mission follows, building understanding incrementally over time through successive efforts. Each generation contributes what it can, trusting that future generations will continue the work toward ultimate understanding. The Moon itself does not wait for our understanding to arrive before continuing its eternal processes uninterrupted. Europa orbits Jupiter every 3.5 days, flexing with each approach and recession from the giant planet. The ocean sloshes and circulates in patterns determined by physics, not by any observer's schedule or timeline for discoveries. Time passes on Europa, as it does everywhere, indifferent to the pace of human exploration activities. The ice shell preserves its record of stresses and exchanges, a document written in cracks and colors and chemical signatures. This record will eventually be read more completely as better instruments examine the surface in greater detail over time. The story of Europa's history, its ocean's evolution, its possible biology, or lack thereof, is written in that ice. Patience and persistence will eventually decode what is written there for human understanding and appreciation. The relationship between Europa and Jupiter continues as it has for billions of years, through gravitational interaction, unbroken. The giant planet raises tides, generates heat, maintains the liquid ocean, and shapes every aspect of the Moon's existence. Without Jupiter, there would be no ocean, no potential habitability, no target for astrobiological investigation whatsoever at this location. The Moon exists in permanent relationship with its planet, dependent and connected across the space between them. This connection between planet and Moon creates the conditions that make Europa worth studying at such effort and expense. The same tidal forces that might have enabled life to arise also created the circumstances that draw our attention outward. Jupiter's gravity reaches across hundreds of thousands of kilometers to touch Europa and keep its ocean liquid against the cold. The physics that operates there operates throughout the universe wherever similar configurations exist, around other planets and stars. Europa as a world has no awareness of its significance to observers on a distant planet called Earth, observing carefully. The Moon simply exists, following its orbit, flexing and heating, maintaining its ocean, presenting its icy face to whatever looks. Our curiosity about Europa is entirely our own concern, a reflection of human nature rather than any property of the Moon itself. We impose meaning and importance on a world that simply is what it is, without any need for significance. Yet this imposition of meaning is itself meaningful, a demonstration of what conscious minds can do with the universe's raw material. We see Europa and wonder about life there, projecting our questions onto its frozen surface from our vantage point on Earth. This wondering has value regardless of whether the answers are what we hope, regardless of whether life is found. The act of reaching out intellectually to distant worlds is part of what makes us human as a species. The night sky from Earth occasionally shows Jupiter as a bright point of light, brighter than any star visible overhead tonight. Orbiting that point of light, invisible without optical aid, Europa follows its path around the giant planet continuously. The ocean beneath its ice covers that moon right now, at this very moment, as the listener rests here on Earth below. The water is there, the darkness is there, the possibility is there, waiting in silence across the gulf of space. The distance between the listener and Europa is vast, approximately 600 million kilometers at closest approach typically observed. Light takes over 30 minutes to travel that distance, and spacecraft take years to make the journey one way successfully. This separation is real and substantial, a reminder of how large the solar system truly is around us. Yet understanding can bridge distances that physical travel cannot easily overcome, with current technology available. Through the work of scientists, engineers, and explorers, Europa has become knowable despite its distance from our home world. We understand its ice shell, suspect its ocean, consider its possible life, plan its future exploration with care and precision. This knowledge exists in human minds, shared through education and communication across our civilization worldwide. Europa is no longer merely a point of light, but a world with characteristics, a place with properties, a destination with potential. The exploration of Europa is part of a larger human endeavor to understand the universe and our place within it fully. We look outward because we are curious, because understanding enriches our existence, because the unknown calls to something deep within our nature. Europa answers that call with mystery, with possibility, with the chance that something remarkable hides in its darkness below. Whether we find life or only learn about geology and chemistry, the exploration has value in the knowledge gained. The ice continues to cover the ocean continues to fill its rocky basin, and Europa continues its orbit in silence. The flexing continues, the heating continues, the chemistry continues in the darkness, far below the frozen surface above. Nothing has changed in the time it took to travel from the surface to the seafloor in our exploration of understanding. The moon persists in its ancient patterns, unmoved by our attention, unchanged by our curiosity about what lies beneath. And so the journey through Europa's world comes to its natural resting place in the quiet depths of understanding. We have traveled from the frozen surface through the cracks and chaos terrains that hint at activity far below. We descended through the ice shell into the darkness of the hidden ocean, filling the space beneath completely. We felt the tidal heating that keeps the water liquid and visited the seafloor where rock meets water in chemical exchange. We considered whether life might exist in those depths and explored the missions that have studied and will study this moon. We placed Europa among its family of ocean worlds, scattered through the outer solar system beyond Mars. Now we rest with the knowledge gained, the questions still open, and the patient continuation of processes that operate regardless of observers. The ocean is there, the ice is there, and the quiet waiting continues as it has for billions of years. The listener may rest now, having traveled far in understanding, while remaining safely here on Earth throughout the journey. Europa continues its orbit, Jupiter continues its dominion, the solar system continues its ancient arrangements, without interruption or pause. The darkness in Europa's ocean is the same darkness that has always been there since the ocean first formed. The silence there is the same silence that will persist until something or someone finally arrives to break it. Sleep comes naturally after such a journey, the mind settling into the knowledge that distant worlds continue their existence in peace. The ice shell of Europa is intact, covering its ocean, recording its stresses in patterns that will persist for ages yet. The water below is liquid, is dark, is possibly alive or possibly not, but is certainly there right now as always. This certainty is a kind of comfort, a reminder that the universe is vast and patient and full of wonders waiting. The exploration will continue tomorrow and for many tomorrows after, but for now, the journey rests complete in understanding. Europa orbits Jupiter in the darkness beyond Mars, its ocean hidden, its secrets kept for future generations to discover. The ice is cold, the water is dark, and the distance is great. Yet understanding has bridged what physical presence cannot yet achieve. The moon is known, partially, imperfectly, but genuinely known in a way that enriches our sense of the cosmos around us. And with that knowledge resting gently in the mind, the vast distances seem less cold, the darkness less absolute, the universe more comprehensible. Europa is out there now. The ocean is beneath the ice now, and the possibility of life continues now, as it has for billions of years. This continuation is a gift of the universe, offered freely to any mind curious enough to receive it with wonder and appreciation. The gift has been received, the journey has been taken, and now only rest remains for the traveler returned safely home.